Alright, hello. Welcome to another module of CS262. We will begin with our objectives and PowerPoint as usual, and then we'll get into the assignment. So let's go ahead and get started. We've got a lot of ground to cover for this one. Our objectives are to apply force to a vector, manipulate vector speed, apply velocity, acceleration, location, force, and mass to vectors, instantiate force vectors, apply multiple forces on motion of an object on the screen, implement mass in a force calculation. Oh my god, that's a nightmare. Well, guess what? It's stupid simple. It really is, because force is just adding two x values and two y values. Your normal location values that we represent as acceleration or velocity. It's just x plus x and y plus y. It really is. It's how you do it though that makes the difference. So let's start with just a little bit on the PowerPoint. Now the PowerPoint, you've got two different templates. You've got your assignment template, which is based on the naming scheme of your book, the nature of code, and then you have your lecture PowerPoints, which is based on a different naming scheme as far as the vectors class is concerned, but it's not an issue. It's not much of a difference between the two. I just wanted to provide you with a template of code to use for your assignments that was close to your book reading. So we're going to go ahead and go through the PowerPoints, and then we'll get started on we'll probably leave assignment number 2 to you, and we'll probably do number 1 together in this video. So let's go ahead and go through the PowerPoints. As I said, there's a lot to kind of cover. Yep, I am recording, so a little OCD for you. Okay, so this takes us into a little bit of a segue from last week, which is the big idea from last week was normalization and understanding that a vector can have different magnitudes but be going in the same direction. So essentially a vector, let's take for instance this example vector of 2, 5. That's going in a direction every frame 2 pixels to the right, 5 pixels down. That is going every frame, but what if we want to slow that vector down so it only moves partially in that direction every frame? And that's where we bring it down to, we normalize it so we can get it down to the lowest value between 0 and 1 for both the x and y values to be going in the same direction as 2, 5. So essentially, if you take 2 divided by 5, you get the value 0.4. Well, that's the ratio of your direction vector. So 2 divided by 5 is 0.4, and if you reduce each of these down by taking, let's say, 2 divided by 10 and 5 divided by 10, you're going to have the same ratio. So when you normalize a vector, you're basically reducing this 2 and this 5 together by the same value with division. So here's the normalize function, but essentially what the value comes out to as part of the calculation using the magnitude of the vector, meaning how large it is, how many steps or how many pixels it moves per frame, is our magnitude essentially. So if this was 410, that would be going in the same direction, but it would have a higher magnitude because it's going 4 pixels to the right versus 2 pixels to the right. Or if it's 10 instead of 5, it's going 10 pixels down instead of 5 pixels down. So we reduce the magnitude of the vector down to its lowest component between 0 and 1. And that comes down to 0.371, 0.928 after you put it through your division calculator. And you come down with a direction vector of 0.371 that's going in the same direction as 2. Of 0.92 that's going in the same direction as 0.4. Or going in the same direction as 5, excuse me. So you take these two numbers and divide 0.371 divided by 0.928, and you get 0.399, which is the same ratio as 0.4. So this value right here is the same as this value as far as direction, just a matter of how much it moves per frame. Okay, so that was kind of where we're at. Now we start discussing how we would apply force to a vector. And as I kind of told you earlier, it's very simple. It's just an addition. That's all you're doing calculation-wise. So when you think about a force is always added. In real life, force is added. It's an added value. So when we calculate force, we add one vector to another vector. So we take the first vector's x and add it to the second vector's x, and the y likewise. It's only within like a measurement system that we would ever apply a negative force, and that's just for calculation basis. And that is because we are simulating the force, a force going backwards with a negative x value or a negative y value. So we just take and add negative values. So a force is always a positive or an addition. If you are going to go in one direction versus the other with a force, you can call it a pushing force and a pulling force, if you will. You add negative values. Okay, so this is kind of a little bit of on our mover. This is the mover that's in the PowerPoint template, and let's go back into that real quick. Let me show you the differences between the templates. This is your Module 7 template. This is the one that your PowerPoint's based on. Now, this one right here, your template 2, the Chapter 2 template, that's the one that you're going to be using for your assignment that uses the same naming conventions as your book, Nature of Code. So we're talking about code that's in this template, Module 7, but that's fine. You don't even have to. If you want to, you can open it up and play with it as we progress. We're going to be talking about code inside of it, but we're going to be applying what we talk about to this template. Okay, so here is our mover class, just like a sprite class. What we have now is, if you see what's in red, these are the things that we need for a mover. We need the radius for this mover particularly, and other movers we may need the radius depending on what kind of sprite sheet you're going to use on it. Our width and height and all our other stuff are in there, of course. One main thing that we need is we need mass. We need to know how big this item is, especially when we apply force calculations to it, because we need to take into consideration big objects versus small objects, because they're going to behave differently when you apply a force to it. Just like in normal life, a big object moves very slowly and takes a lot more force than a small object. Our location vector is going to be dictated by our velocity vector, and then our acceleration vector, our velocity vector, is going to be dictated by our acceleration vector. Those are all pretty much standard calculations that we'll probably review and go over again as we progress. So this is kind of the object that we're going to be working with or working towards being able to create. Okay, so the first step is to instantiate the mover, and then what we need to do is, once we have the mover instantiated, we need to update it by adding a force to it. So this example is taking a vector of 0.4 and 0.1, which is going to be a force, and this is just a motion vector. That means that this would be a force that moves 0.4 pixels down and 0.1 or 0.4 pixels to the right and 0.1 pixels down. And then we take and we apply that force to the current object. And then from there, here's the normal calculations that do not change ever. We take and we add the acceleration to the velocity. Then we add the velocity to the location. and then we set the acceleration back at 0. Now this is extremely important, this step right here, because nothing will work without it. And in fact, I've even had high school physics teachers have to come to me to get this part of it. Make sure you remember that you're simulating motion in real time, and acceleration is an intermittent thing. That means that it is determined by time. So you have to have a component where acceleration resets itself, and that is every frame. So since acceleration is only only exists within a certain slice of time, it's not an expression to describe something over multiple slices of time. That's what velocity is for. That means that your acceleration needs to be applied every frame and reset to 0. That's what makes it all work. That's where the magic happens. Then we have our bounce edges, which we've already talked about, and then of course some statements to constrain the velocity of the object so that it doesn't go beyond a speed of 20 pixels per frame. Okay, then we draw. This is pretty self-explanatory. We use the location that has been manipulated by the acceleration and velocity. In this case, for this example, we draw the radius. Okay, and then of course the image if it's needed. All right, one thing that is added to this template is the ability to use acceleration within your key state switching mechanism. Now you notice here's something that's very key here is I take a value, and I just picked just one that works, but I divide it by frames per second. This is kind of just a little hint on what one thing that you have to do within games is you're creating a world, and the world has to have rules that are pretty much part of the world itself, which is obviously your time. The time is it. So movement, you want to somehow in some way work with the frames per second to make it happen appropriately within your environment, especially when you get down to things like some higher levels of collision detection. You got to take into consideration your frames per second, the amount of pixels you're moving a lot in those calculations. So I always try to constrain by frames per second. I don't suggest that you worry about that too much. Just keep it in mind. All right, so here we are. Acceleration is where it all begins. Velocity is accelerated by, is adjusted by acceleration, and then of course location is adjusted by velocity. So when you have an update function, you're always going to update velocity with your acceleration, and then update your location with your velocity. And this is literally just taking, let me give you an idea of what this add function does. It's really simple, and we're going to actually, let's see. I think maybe the add function is in the library, so let's go ahead and get NetBeans opened up and get that template downloaded, the one with the code that we're talking about right now. So I'm going to go ahead and download that code, and now the template that I'm talking about, let's go there before I pause and get things ready off screen. The template I'm talking about is the Module 7 template. That's the one that I talk about for PowerPoints. This one is your homework. So let's download this one and talk about some of the inner workings of it, and along with the PowerPoint, of course. I'm going to get that one ready to go, and I'll pause it and bring it back. Okay, so we're back. Let's go ahead and look at that PowerPoint template that's available to you. I'll zoom in. Right now I'm going to open up the mover object, and inside of it we will see the code that's in the PowerPoint. And here is the key, the add function. That is inside of the math vector class that for this particular version of the code is called pvector. Now, I wonder, is it pvector? I may have told you wrong. Maybe the, okay, so one of these templates, one or the other, uses the naming convention of your book. The other one uses the one I like. But it's all the same stuff. So here is your add function. All this other stuff inside of pvector, just ignore. Because there's only one that really is used and it matters. And that is this add one. So we send this add one. We run it on top on the current vector. So when you're inside of pmover and you call, let's see here. Let's go back to the mover class. Let's see this. Okay, so when you say velocity.add, you're saying add this value, this x value, and the acceleration x value and the acceleration y value to the velocity's x value and the velocity's y value. If you look at that math vector, it's going to be one of these add functions because it's not going to be these ones. Oh yeah, it's this one right here. It just returns a new one, and you just pass it one. So it takes the current x, which is the one that it's being applied to, which when you look at the code, it's velocity. So you could just replace that with this dot velocity. So when you're over here, this means the current vector that you're applying it to, which is this dot velocity dot x, added to the other vector's x, which is the acceleration's x. Then you have this dot velocity y added to the other y velocity, which is the acceleration velocities, or the acceleration dot y. So I would highly stress that you understand what this dot means, especially in the terms of an object. And there in other languages that you can use as part of your search is C#, and C or C++. Those are the languages that use this, and JavaScript was built using C and C++. It's a C-based language, so they use the proper term this for objects. And of course, it was part of your reading too. Okay, so let's go ahead and go back to the PowerPoint here. Okay, if I can actually find it. There we go. All right, so when we're going to apply the acceleration, adding the x and y values to the velocity x and y values, and then the resultant value goes into the velocity. Then we add the velocity values x and y to the location values, and the resultant value goes back into the location. Then we set the acceleration back to 0. Remember, this is a time-based system, and we've got acceleration is only something that happens within slices of time. All right, so here is where we actually apply force. And the force is kind of interesting because it just adds x and y too. So it's no different than when we say add acceleration to the velocity, because isn't acceleration a force? Yeah, so literally when we apply a force, we're just doing the same thing as we do on this line. So we're just taking, and when I say this dot apply force when, it's the only thing that's going to be different between the acceleration versus velocity and the at function is that when we take into consideration like mass and stuff like that. But when we apply this when vector of 0.4 and 0.1 to our current mover's values. Here's what we're gonna here's what it'll look like. We're gonna get there in a bit, but that applyForce function is just going to be doing an addition of the two x's and two y's, just like your velocity these equations do. The only difference is that we're going to apply a mass, something to do with mass on that. Using force is pretty simple. So the applyForce function, here's how it looks. What we're going to do is we're just going to take the force vector and add it to the acceleration vector. And that means that we just take force.x plus acceleration.x and force.y plus acceleration.y, and then we have a new acceleration. So it's exactly the same. The only thing that's different is that we want to take that force and we would want to divide it by the mass of the mover. That means that we are scaling down the force. The bigger the mass, the larger the mass value, the smaller the force applied to the acceleration is. So that's going to be a division. All right, so this dot acceleration here is an example of the add function. So let me kind of give you an idea of what you're dealing with. When you take two forces and add them together, let's say that the force 5, 2 and the force 3, 4. So when I say force a vector, I'm kind of using the same thing in a lot of ways. But all it is when you add them together, it's just like a vector add. You take 5 plus 3 and 2 plus 4. And the resultant value is 8, 6. Now when you think about it, let's say that two things collide. One's going this direction, one is going this direction. Let's say they collide. And you can think of what would be, if they hit together, what would be the resultant force or direction. And we've all seen balls hit other balls in the air, stuff like that. That's the behaviors and what happens, just like when you're playing pool and you hit your cue ball against another ball. The behavior of the resultant force is going to be somewhere between the two. And you can kind of see it visually happen. If something is going steep to the right or shallowly down and another is going steep down and you add them together, you're going to get something between the two. So you can see how this angle is a little bit, it's sort of like this one and sort of like this one, but it's in between. Okay, so when we're dealing with adding force to acceleration, which remember, when we add force, we do it to acceleration because that's going to be, you're adding force for just a slice of time. That's it. You can add that force every time in the slice of time, which is what you have to do until that force is done being applied to that object. But remember, acceleration then applies to velocity, which then applies to location. And then that force added within that slice of time will have an effect on those objects, just as long as your acceleration starts off back at 0 again, as it should. So the add function is just showing x plus x, y plus y. So force.x plus acceleration.x equals acceleration.x. Force plus y plus force.y plus acceleration.y equals acceleration.y. Okay, so here's where it actually ends up happening. We're going to basically think about what would be a resultant vector of a mover given two forces. So if we have a force of wind going in this direction and the force of gravity going down, and the mover is going in this direction, that means that the mover should start going like in this direction or something like that. So it's going to have some kind of application. So we're going to just take the acceleration and add the x and y values of the wind, and then the acceleration of the gravity values, and then what we'll have, so that acceleration accumulates. So remember, we're going to be applying these forces every frame, and acceleration is going to zero out every frame, but before it zeroes out, it's adding to the velocity. So every frame we're going to be adding a 0.4 and a 0.6 force. All right, so here is an example of kind of what I was talking about. If you got a mover going in this direction, down like this at 6.9, you're applying a gravity force to it and a wind force to it. You can think of, well, gravity is pushing down on it and wind, so that means that this vector is going to become straighter and moving like this, because we've got wind but gravity is, depending on the values. So you can see the resultant value of our 2-3 mover after this force has been applied to it. So this is kind of all the equations laid out for you to follow after like 10 frames, and we're already probably a half hour into this. And a lot of you have talked about keeping videos short as possible, because you should be doing your reading and whatnot. We're going to go ahead and move on. Mass is where everything kind of comes in. Your actual application of your force. The only thing that's different between the add function and your add force function is the mass calculation. Other than that, force is just another addition, just like velocity and acceleration and location of velocity. Okay, so here is how you would deal with the mass and the apply force function. You take the force x. Excuse me, I just messed everything up. You take the force x and the force y, and you divide it by the mass of the object. So essentially what you're doing is you're taking away from the force, because the larger the mass is, the less force it's going to have. So you're just going to do a division. That's what this div2 means. It's going to be just literally division. And here's the division function you'll find in the vector library. You just take the force x, that's this dot x, is equal to this dot x, or force dot x, divided by the number you're going to pass in, which is this dot mass. Then you take the force y, divide it by the mass again, and that gives you the force y resultant value. So essentially you're just scaling down the force based on the mass with a division of both the x and y values. And then, of course, after you've scaled the force down with mass, you can take and do your acceleration. And then, of course, your acceleration, remember, acceleration will reset after it's applied to the velocity. So remember, force is only applied within a slice of time. Acceleration is what is used to change an object's velocity, and then velocity for location. All right. I think this is an example of taking a mass of 0.5. So you think about a mass of 0.5, that's a really small mass. And if we take this small mass and we divide it with some numbers, we get some larger numbers. So small values of mass really change things. And what you're going to want to do is you're going to want to go in and just start playing with things and playing with different masses and see what happens to the force vectors and your acceleration profile. And what you'll see is that things that are large tend to move or the force applied to them tend to need to be greater because you're dividing. But really small objects tend to move fast, be very responsive to other forces, just like in real life. All right, so let's go have some fun. I'm gonna just go ahead and pause it, and then we'll go do our steps, and hopefully I can hit this within an hour. We're doing pretty good, not bad. All right. So another 33 or maybe it might be a little longer coming up. All right, let's go ahead and resume with my favorite part. Let's go have some fun. We're going to download the template here that's prepared for you based on your the nature of code naming conventions, I think. We'll find out. Actually, I think, no, it is. Okay, so let's go ahead and open that up in NetBeans, and we'll just do a once over of the code, and then we'll get going on the steps outlined in your assignment, at least for step 1. And let's go ahead. Oh, that's the other module. Did I open one? No, I didn't open it. Okay, open. Okay, we're looking for chapter 2, template underscore chapter 2. Chapter underscore 2. Okay, here's your chapter 2 underscore template. Now that chapter 2 is for your nature of code chapter 2. So you got templates just for the nature of code book. Okay, so we have our index that's going to contain the most important part of everything, which is your mathvector.js, which the only thing that we really use a lot is the add function. All the other stuff is there so that you know what are the different things you need for a fully working game. And being that the prerequisite for the course does not include higher levels of math, that's been supplied for you. And a lot of the stuff that we talk about, we won't be able to go into deep detail, but that'll be for some of the other functions that that are beyond the scope of the course. But they're there for you so that you kind of have an idea of the things you need. Okay, so then we have the mover class, which is just our sprite that's automated. And then, of course, canvas. So let's look at canvas. Okay, so in canvas, what we do is we are going to create a mover array. We're going to create an array of movers. So I should have had that in your reading. And then we are going to take that array of movers. And what we have to do first is we have to initialize every mover in the array. So we're going to create 100 movers. So first you declare a mover object, and then we have an array. Now, I don't think the array part is going to be part of our assignment, but we'll see. We'll continue on. But what this mover array does is it just instantiates 100 of your movers. And when you declare an array, of an object that we're going to call movers, you got to actually go in and create the 100 movers, just like we created one mover here. So that's got to be done in runtime code in a function. Right outside here, this is what we call definition code. It also has an aspect of runtime to it, And so this is usually what's only can happen outside of functions, but languages have now made it so they can allow you to do some simple things outside of a function. So when I say runtime code, I'm talking about code that's in a function. So we have to actually instantiate those guys in a for loop. And oh, you know what? I'm thinking C and C++. You can actually do whatever the hell you want in JavaScript. You can put a for loop out here at file scope too. But you know, let's be organized. Okay, so we declare the array, and then down here we have a function called setup that's actually called here setup, and this function just quickly instantiates those movers. And it instantiates it with some random values. Okay, and then down here is our diagnostic. Let's just get rid of this unless it does any kind of anything. No, it's junk. Okay, let's get rid of that junk. Let's move the setup down here, just because this is just ridiculous. Let's call the setup down here. Oh wait, we got to set up before the game loop is called. I even put comments on that. Okay. Now we instantiate the movers so that we have them ready, and then we do our stuff. Okay, our clear canvas. Let's go ahead and make a few modifications to the clear canvas because this offset just drives me insane. Let's do a 0, 0 starting. And get rid of this. This just makes a box where a little box where it's not being updated as quickly. So, and then diagnostics are gone, so we get rid of that. Let's keep our calc FPS because we need our frames per second, possibly. And I think I should have that as a global value. It is. It's there. And we have our date value. Okay, so here's kind of what we have. Well, let's see what it does first. I guess we probably should have done that before we started tearing it apart. Okay, well, let's see if something actually does something. Okay, let's go ahead and hit play here. And let me choose this guy. Okay. All right, so we have an array of movers that are being drawn in this corner. All right, so this array of movers we're going to actually make behave differently based on their mass, and the larger they are, the more mass they're going to have. So when we instantiate these movers, what we're doing here, let's look at the mover class. Well, let's look at the mover class and the math vector class. So let's actually come back to the mover class. Let's go ahead and go to the math vector class. So the main thing that we're going to be using is the add function. And here is the big bug, and you'll see this in some of the other code. These are functions that are meant to behave differently. So one of these, and JavaScript doesn't handle same name functions very well, even though they have, well, this is just a glaring error, and it needs to be fixed. So you will find this error in a few other vector classes that will be given to you for templates. So just come in and do like an add to, just add a to there, or add second add, or alternate add, or let's just be simple and say it's add to. They do the same thing, it's just one behaves differently than the other. The first one returns new memory after doing the addition. The second one does not return new memory and just modifies the existing memory. And if you were to do add to versus add, this add function is the one you want to use because it's more efficient. As soon as you do this new, you're screwing things up, because what happens is the garbage collector is always looking to see when you're done with that memory, and it frees it up. So every time you use new, you're just adding more for the garbage collector to do, which reduces your efficiency. And for game programming within managed systems, such as C#, Java, JavaScript, If you're not doing if you've got a memory management system, you got to do what's called pooling your memory. Create all your memory at the beginning of the game and use or reuse that memory through memory pooling. But in any case, I'm getting beyond where we even need to be. In any case, one of these add functions needs to be fixed. And preferably, we'll be changing the applyForce function to match whichever one we end up working with. Okay, and then we got our mover object, which is just your sprite object, and we have the applyForce here, and we have mass. So we're going to actually build the applyForce function. And we're going to do that from the example seen in your Nature of Code 2.1. Okay, so right now we have something that does nothing. We are just literally instantiating 100 movers. So let's go back to the game. We instantiate the 100 movers from our setup. That happens first. Then we go into the game loop. We call the update and the draw. We go to the update. The update calls the movers, each mover's update function. And the draw calls every mover's draw function. So this file is pretty much done. We don't need to play in here at all. We're going to be messing around with movers. And to do that, we already have the update and the draw functions being called. To do that, we've got to do it inside the mover class, especially when we're applying physics to it. Because in our game, update, or when we update and draw our movers, specifically when we update it, we're going to be applying some wind and gravity force to it. But we're going to do it inside the object. You would actually it would be preferable to apply force here. So this is the best place to apply force, but we're going to do it. We're going to do some learning steps and we do it inside the object, and you can take it outside as you kind of progress, if you wish. So let's go ahead and go into movers, and I've already kind of given us some hints here. We have some topics or some comments here that give you some instructions. So we got to implement a velocity vector here, and we got to implement an acceleration vector. Then we have to apply those vectors. So through this code, I've got comments here that we're going to be actually working with. Okay. Looks like this looks like this is a comment that we need to follow too. Okay. So implement velocity vector here. All right. Well, when I say implement, that means to create. So let's go ahead and say this dot velocity equals. Oh, we forgot something, didn't we? I'm sorry. We didn't talk about the instantiation of a mover. Let's just come back to this in a second. Let's go back over to here. And actually, we got to look at the movers. Okay, so what we send a mover when we instantiate a mover, we send it its mass and an X and Y value. We go back to Canvas and we look where we do our setup. We are setting up a random mass between 0.1 and 5. And we're starting at location 0, 0. Now then, let's look at the mover draw function. So we go into mover and we go to draw. And we see here that we create an ellipse, but it's taking the mass of the object times 16 for the radius of your ellipse. So the mass of the object is dictating how large the ellipse is. So this is where we're going to apply force with mass. So we're actually building a circle where the larger the circle is, the more mass it has. And that's reflected, and we're going to reflect that both in how we draw it and how we apply force to it. So it's really a simple ellipse using mass to determine the radius of the circle. And the mass of our object represents how big. So our movers are just circles. Small circles and little circles. And if you can see here, you see a whole bunch of circles being drawn of different mass. And it's not until we apply force and gravity to it that we're going to see something happen. Okay, so back to the fun. Let's go back to, well, all right, I lied. Let's go to instructions and then fun. I want you to know that these instructions are literally in your assignment page. So here is your first instruction for step 1, and declare and initialize velocity and acceleration vectors in object mover. Okay, so then we're going to complete the apply force function, modify the update function of the mover object to apply force and update location, acceleration, and velocity vectors as seen in example 2.1. Modify the existing code in some way, such as changing colors, position, or additions. You're going to do that on your own. Step 4 you're going to do on your own. And I'm going to leave you with step 4. Oh no. You're going to do step 4 on your own. Then it looks like we're going to implement... We're going to go into steps 1 and 2. I'm going to have probably... Oh, you'll do step 4 and step 2 on your own. That's how I got it set up. Okay, so... Let's actually put those in bold. If I can remember how to do it. All right. Those ones you guys do on your own. Okay. All right, let's get to it then. The first step, implementing velocity and acceleration in the project mover. So we're going to go in the project mover, and we're going to create a velocity vector. And our velocity, our location is going to be set by what we pass into the object, which is 0, 0 when we create the mover. The location, we're just going to apply with that X and Y. But the velocity, we're going to start out at 0, 0. And we're going to do the same thing with acceleration. Okay, so we've got our velocity, acceleration, and our location vectors. Hopefully I have not misspelled that, but that's good. Okay, so the update function is going to be important for a few things, and that is that we got to follow the rules, but let's not get beyond our steps. Let's go back to our steps. What's our next step? Step 2, complete the apply force function. Okay, so as seen in example 2.1 of your book, didn't we just see a PowerPoint with that done for us? I think we did, didn't we? Oh, didn't we get a template that had it done for us? I think we did. All right, where is that silly template that we were messing around with? Module 7 template? Okay. Let's see. Oh, so it's done for us, but we got to make sure it works within the naming conventions of your book. So, because the math vector has, if you can see, your math vector has p vector. We'll see if the other one is the same. It might be the same. Let's go. Oh no, I'm looking in the other one. Duh, I'm silly. Okay. math vector for this one. Yeah, okay, p vector 2. That's one. Maybe that is the other one. What is the math vector called here? It's called p vector. Okay, I guess we're doing all right. Okay, so the applyForce function has already been done for us in that module 7 template. So let's just grab that one. So we're going to go to mover.js. Oh, look at this. We've got, we can steal our constraining. We can grab all of this. Okay, so let's grab that and let's bring it over here. Not to math factor, to mover. And let's put that in the update. Okay. So that we constrain our velocity vector that we just created. We take our acceleration, add it to our velocity, take our velocity, add it to our location, reset the acceleration at 0, 0. We don't have bounce edges here. So let's do check edges. We might have bounce edges, but this code is using check edges. So we'll put that there. And then we will use the constraint. Okay, so let's look at it before and then after. Here is after. Here is before. Okay, so this is then added, the code added in that we stole from the other template. And instead of bounce edges, we're going to do check edges, which is code that's in here somewhere. Here it is right here. Here's our check edges. So that's already set up for you. Constrain the velocity like we should for every moving object. Do the same thing for velocity and location. Okay, so that's update step. I think we skipped a step there. Okay, now let's go to the applyForce. Let's steal it from over yonder. Where's the applyForce? Okay, we may have to change this. It's probably not going to work. But we take the force and we do a division of the mass, and then we add the acceleration. Okay, so now we're going to go over to our mover here. Okay, so receive a force, divide by mass, and add to acceleration. Okay, force. Force is coming in as an argument. We take it and we divide it by the mass. Is there a division 2 function inside of our current math vector? So don't go to the one that we're stealing from. We're done stealing from that. Go into your math vector class and make sure there's a div 2. Oh no, look at that. It's a bug. There's 2 divs. Okay, it's not a bug. I do that on purpose just to make sure people are paying attention and actually looking into their code. And here's a little known secret. The code that you see posted, that everybody posts to help people, something in it is always changed to make it not work. Just get used to it. Okay, so let's call this div 2. Okay, so what this does is just takes an x and a y value. Oh, look at that, another bug. That's got to be y. I'm sure you're paying attention. Okay, this dot x is equal to, oh, look at that, another bug. This dot x divided by the mass. This dot y is equal to this dot y divided by the mass. Okay, so now we have a div 2 function working. Let's go back to our index. Oh no, not our index. Our math vector, we're done with that for now. We may have a bug. It may not work very well. Okay. But we're going to test it out. Okay, so receive a force, divide by mass, and add to acceleration. Check. Port and complete apply force function of mover as seen in example 2.1. That's what we just did. So we take, and when we apply force to our motion vector, we're going to be applying it to the acceleration vector, and we're going to take that force and we're going to take it down by a ratio of dividing it by the mass. Then we apply it to the acceleration, which the acceleration is then applied to velocity when it's next updated. Then we add the velocity to the location and then reset the acceleration to 0. Okay, now next. Okay, so did we implemented the update of velocity, location, acceleration, and apply the force of wind and gravity before acceleration and velocity update. Oh, apply the force of wind and gravity before acceleration and velocity update. That's right here. Okay, so here we go. Let's create a wind vector. Okay, and let's say that the wind is blowing to the right. And let's say that we have a wind also blowing at us from above. So what we can do is we can instantiate a force vector here, but remember that it shouldn't be done here. It should be done outside of the game. This is just to show you to be as simplistic as possible, because by golly, this is getting complex. If you're not starting, your head is not starting to hurt yet. It's going to take a couple overnight sessions as far as learn, sleep, retain, learn, sleep, that sort of thing. And literally, it actually takes you going into sleep and waking up, because those physical connections can't be made. It's an actual physical connection where you're building new neutrons. And as you get older, you just get smarter and smarter. Okay, so we're going to actually do this here. So we got to create a force vector of a wind. Okay, so let's say that we're going to create a p vector. Call it force, wind force. And equals new p vector. Now remember, this is not the way we should be doing this for efficiency. We should be reusing a wind force that's already created and pooled in our main canvas page area, our game loop area, because this is absolutely horrible to do new here. Okay, so let's give a value to that wind. Let's say that it is blowing at 0.5 pixels a frame and to the right, 0.5 pixels a frame to the right. And let's say it's really strong gravity. Let's say it's 0.9 pixels down. Not gravity, but wind down. Okay, so it's going to go to the right and down, but it's going to go down steeper than it is going to the right. Okay, so now that force vector has been added, now we just need to apply that force. So we run that apply force function, and we say wind force here. And then what happens is the wind force is the force vector 0.5 and 0.9 is going to be added to the acceleration. So the current acceleration will be 0. So when it's done, it's going to be 0.5 and then 0.9, and it's going to start moving. And then next frame, we're going to add another force to it, and it's going to be 0.5 and 0.9 and begin moving. And it's going to go up in increments of 0.5 and 0.9, steadily adding speed, because we're applying that force every update until that speed goes beyond the 20 frames per second that we have set here, and we constrain it. So we apply that, we add this, so essentially it's going to be, in the end, for the very first run, locations X is going to be added by 0.5, locations Y is going to be added by 0.9. And then what you'll see is the interplay between the velocity and the acceleration is going to take into And of course, when we take into consideration the mass, we're going to get different behaviors. So I think we're ready to test this. Let me make sure that we don't have any other steps left to go. We're on step 3 right now. We're on step 1, sort of. We need to create another force vector called gravity. That's fine. You know what we could do? We could separate it out into 2 different vectors, one for wind and one for gravity. Well, let's just play with what we got for now. We could just say that that's our gravity, in other words. Okay, well, I didn't expect it to work right off the bat. It's totally dead. Okay, so it died, which is fine because I knew that we had to finagle a few things. We got to make sure some values are being set correctly and set the debugger. And this is something that is expected that you guys do often. This is something you got to know. You got to understand what's going on. And then you got to investigate when it goes wrong. So we're going to be dealing with the mover vector. We're going to go to sources. Why do I not have a mover vector? Oh, because it doesn't know what a mover is? I got a capital N there. Really? That's the only problem? How did that happen? Okay. Let's go to my canvas. Well, let's look at mover first. What is it? Is it a lowercase? No, it's an uppercase M. Are we including it in our index? Mover.js right there. Okay, so evidently something's wrong with mover. Okay, well, let's look at the bug. Let's look at what it says here. Look at the console. Should have gotten something on the console output. Here we go. Mover is not defined. Okay. I'm pretty sure that we included it. Okay, I'm going to pause so you don't have to, and then I'll give you the solution when we get back. Okay, well, typical of me, I was actually writing C++ code or C code. Yeah, so this should be in your update function. This should be var, and that's why I wasn't reading it. It was unrecognized. Okay, so var winForce equals new p vector. Okay, so we're ready to roll. Hopefully, cross your fingers. Duh, of course. All right, back to the debugger. Okay. P vector add. Okay, it looks like we got to get rid of that add function. It somehow does not like it. Oh, it's missing. No, it's not. Something's wrong with that. Okay, well, let's get rid of it. Evidently it's not working. Let's just go ahead and go in there and get rid of it. Okay, so probably something, who knows what's going on with that. JavaScript is a little temperamental. Okay, so let's go up. So I'm going to go into the math vector, and evidently it does not like that add function. Oh, probably because it's clashing with that one. Okay, well, let's just get rid of it. I think it is clashing with the other one. I got too many adds in here. I think add 2 is going to do what we want. Because I think I got another add down here. Yeah, this is a prototype one. Okay, we might want to get rid of that one too. Okay, save all. Okay, run it again after getting rid of those 2 extra adds. Then go to your developer tools again. Let's see what's wrong. Add is not a function at applyForce. Okay, so we called that add 2 now. So let's try the add 2. So let's go back to our code and let's go to mover. And then inside, oh no, it's going to be, yeah, it's going to be mover. And this is going to be add 2. All right, you could rename yours to add since we got rid of all the other ones. Okay, now save all, run. Okay, developer tools, velocity add. Okay, we're gonna have to do add 2 to them all. Dang it! You know what? It's better just to get rid of the 2 and go backwards and go the other direction. Okay, so let's just get rid of this 2. Go into math vector and get rid of, since we got rid of all the other crazy adds, let's get rid of this add 2. Let's get rid of just the 2 and leave it as add. Okay. All right, now I'm gonna clean up a little bit here. Go back to developers tools. Oh, we gotta change it back in the other place. We got to go back here and, oh no, we got to go to the mover and add. Okay, so we're good. Okay, so let's go look at the other errors. Acceleration.set. Okay, well, you know what? We don't really need the set function. That's what it calls for in your books code. What we could do is we could just add set x and y to 0. So it's looking for the set function in the p vector library, and evidently it's not there. Okay, well, let's, instead of adding the set function, let's just do this. Let's go back here to mover, and instead of running set, this is going to need to, I would suggest you try to actually add that to the p vector object if you could. That would be a good test before you do play around with get something that's working first, and that is do this. Simple. You don't need a function for it. In fact, all this stuff right here you don't need a function for. It's just literally doing add. It's just adding x and y's together. That's all you're doing. Okay. That does that one. All right. Now let's go on and see what the next error. Oh, whoa, look at that. It's working. Magic. Awesome. Okay, so you notice here that those little ones are really going crazy and the big ones are not being moved as much. And that's because of that mass, the mass, scaling down your mass. And you can play around with this quite a different ways, and one of them would be to let's see, let's play around, and I know I gotta let you go here, probably go play. We got what we needed. Let's do this. When we do the force, when we create the wind force, we could break this up into also a gravity force, and we could just do a 0 here. And then what we could do is we could do a var gravity equals new p vector. And then we can do a 0 there and the 0.9 here. And then we apply both forces. One is just an X force, and the other is just a Y force. And another thing we can do is, what if we wanted to scale down the mass thing a little bit more? We could look at how we're actually doing the mass calculation. And we could decide that this div 2 is going to work a little bit different. We could say, instead of this dot mass, we could say this dot mass divided by FPS or something like that. There's a lot of different things that you could do. We could say minus 1.0 here, minus 1. So, or plus 10, or plus, let's do this. Let's do plus 100. Let's see what that's going to do. Because that's going to give a large mass and make it so that that force... Okay, so you see here that's moving very slowly because of our mass calculations. So there's not much of a speed difference because they're coming in right at the same ratio about. Because all those 100 movers are being drawn together in one big clump right now. So that's not really cool. Okay. Let's see if that will work better. Yeah, okay, so we're getting a little bit of a differentiation between the different circles. There we go. See, the small ones are starting to break away. The very small one, because of the mass change on it. It's so cool when you can start doing this stuff because, I mean, it just comes alive. Look at that. All right, you guys have some fun with this. Let's see. Some things that you could do is just delete all the crap out of p-vector and not even look at it and rebuild all of this up from ground up on your own with your own naming conventions to get a better understanding of everything and that in between your reading of nature of code. But you have a working example, a walkthrough. I think it's left to you now. So here's what I want to see for some changes. So you're going to say, so you're going to be doing the step 4 and step 2 of each one. I want you to modify the existing code to such as changing colors, positions, or additions. Now that actually can be rewritten because that's all the last step. Modify, because this step 4 is just redundant. Okay, now because you can just turn it to something all as one assignment. Actually, step 5. Okay, modify the existing code in some way, such as changing colors, positions, or additions. I want you to add one force that you create. Change colors and positions. I've had people make it so that the movers are all changing colors, flashing colors as they're moving around. I've had them change how the way it's drawn so that they use some pretty slick stuff from the drawing library. Any kind of change. What I want you to do is, hey, what if change? You know, push yourself and give yourself your own little project there in the direction of something you need to learn or you want to know or you want to verify. Specifically, verify is a good one. But come up with something of your own investigation. And here's some examples of that. Make sure that it is definitely made note to me of what you did to make it yours. All right, that's it. Thank you guys. It's really, we're getting into the fun stuff now. Oscillation is going to be a chore. I want you to start looking into implementation of polar coordinates. Until next week, thank you.